is Galyna Livshyts from Georgia Tech, and the title of her lecture is Gaussian Isoperimetry, Symmetry, and Related Things. Please, Galyna.
Thank you very much. Thanks to all the organizers. It's a very interesting conference. Hi, Mark. Yeah, I will talk about a bunch of things. Let me start with mentioning some notation. And like I said, some of this is, I don't expect you to memorize it, some of it. But like I said, there is a link that Omi had just posted in the chat. And if anybody wants to scroll back to the notation, you can scroll back to the notation slide or to any other slide. Lebesgue measure I will denote by just two straight lines. Gaussian measure I will denote by letter gamma. It's a measure with the density written here, just in case. Minkowski sum of sets. So mostly I'm working just in Euclidean space Rn. Nothing more complicated than that. Minkowski sum of sets is defined in the way that's written here. By psi, I will denote Gaussian CDF, which is written over here. Some people occasionally use letter capital phi. Sometimes it's psi, sometimes I'm not sure. So anyway, I use psi. And there is a few more special functions written here, just that will be mentioned in the talk a few times. So let me start with reminding you about the Brunn-Minkowski inequality, which tells us that the volume of sets in n of barrel measurable sets in n-dimensional space of the Minkowski average of sets is bigger than the average of volumes if you raise the volume to the power 1 over n. It tells us basically that the function of the volume to the power 1 over n is concave for the Lebesgue measure. This inequality is very useful. I will mention also why it's useful, but in particular, the model application is a classical isoperimetric inequality that tells us the following. Suppose we consider all possible sets in Rn of given fixed volume, which set has the smallest possible perimeter. We've heard a lot of such things in Emmanuel's talk, of course, and in this case, it's very well known for many years, at least since 1838, that it's the Euclidean ball. And from Brunn-Minkowski inequality, you can prove it really easily in my view. Here is a one-line proof, provided that you believe that the perimeter can be defined in the way that I defined it here. You can estimate, so basically the perimeter is nothing but the limit of the annulus of K divided by the width of the annulus. Sorry, perimeter. I'm not going to draw. So this is how you define the perimeter in the first equality. You can estimate it from below using Brunn-Minkowski inequality. Immediately you get an expression on the right which corresponds to proving this Brunn-Minkowski inequality. This is quite standard. Let me now put the corresponding slide in regards to Gaussian isoperimetry. So for the Gaussian measure, there is this really cool inequality called the Erhard inequality, which tells us that if I take the Gaussian measure of Minkowski average of sets and apply the inverse of the Gaussian CDF, psi, which is written in the notation slide over there, then I get that this function is kind of also concave. So this in particular implies it follows from and implies, and there are all kinds of connections, but here is one way in which it implies the Gaussian isoperimetric inequality, which tells us that if we consider fixed number a between 0 and 1, between 0 and 1/2, let's say. Let me just put 1/2 just in case I'm not sure, because yeah, I'm nervous here. Okay, one thing I didn't check. Okay, 1/2, just in case. Okay, then the set of the smallest perimeter is half space, this left half space of the same measure. And the half spaces minimize the Gaussian perimeter. And here is a pretty simple, again, a little bit more, I would say more complicated than in the Brunn-Minkowski case because of the lack of homogeneity, but still simple enough proof. You could, I highly recommend the survey by Rafael Latala on this subject that is very expensive. So anyway, you could derive the isoperimetric inequality from here. Let me, again, I also did my homework, like Max had one slide like that, and Emmanuel had one slide like this. I also have a slide about connections to concentration of measures. This is a very small sample of things that you could use Erhard, Gaussian, and Brunn-Minkowski for. You could get the sharp version of Gaussian isoperimetry. You could get the non-sharp version of the isoperimetry on the sphere if you use Brunn-Minkowski inequality. These are like concentration type results. Right? If you take a set, you know it has large measure, you enlarge it a little bit. You enlarge it, you make it just a little bit fatter. How much does the measure change? So this is a concentration type inequalities. You can estimate moments of norms of low-concave random vectors, which is a very useful result. It follows from Borel's lemma, which in turn follows from Brunn-Minkowski inequality. So this is like a super small sample of things for which it can be useful. And hopefully it will justify me talking about all of the things today. Are there any questions so far?
Everything is clear.
Okay, thanks. Good. Let me. The method, I will not actually, unfortunately, mention anything in detail in this regard, but let me just say that the method that we use here is based on considering local versions of all these Brunn-Minkowski type inequalities. Namely, suppose we have, let's say, some convex set and some measure mu. We move our convex set in time. Namely, we push with some constant speed along each normal, so it's like a gradient flow if you want. We consider family of bodies KT, defined by this flow locally. In geometric flows, often they are concerned on the behavior of the thing when t goes to infinity. We're absolutely not concerned of this. We only care about what happens for a very small period of time. If the convex set is strictly convex, you can always push at least a little bit. Then the fact that the inequality of this type holds, as in the second bullet point here, is equivalent to showing that for any A, if measure of case A, we can estimate the second derivative of f over the first derivative of f from above. This is the isoperimetric profile, if you want, from above by the derivatives of this function. So these things have been, in principle, like if I go in very general terms, I'll have to go to, I don't know, Lagrange and Leibniz and Cauchy and, all those, Bernoulli, Riemann. But roughly, here's a sample of references that I put on the slide that are relevant for this method. Colisanti considered this method to derive from the Brunn-Minkowski inequality upon Poincare type inequality. In my view, the most influential paper in all of this realm is the one of Kolesnikov and Milman from, I think, 2018, where they actually gave the L2 proof of the Brunn-Minkowski inequality back via studying the local version. So this is a very important paper that has influenced, in particular, everything that I'm going to talk about and many other developments in math. So, and there are some other papers that I wrote here as well, but yeah. This was very briefly about the method. So the very interesting question, I'm not claiming it's the topic of the talk, I just think it's a very interesting question, is the question of Barthe, O'Donnell, Hellman, I think Morgan asked something like this. I'm not quite sure how to exactly call it, after what names, but the question is, suppose we assume that the set is symmetric about the origin in Rn, and we fix its Gaussian measure. What set minimizes the perimeter? And Hellman conjectured after Barthe a long time ago, O'Donnell, they asked this question, so Hellman found a very interesting plausible conjecture that says that, in fact, round case cylinders minimize the perimeter. And by round case cylinders, I call products of k-dimensional, n minus k-dimensional spaces and k-dimensional balls. So for example, a strip is a round case cylinder when k equals to 1. A ball is a round case cylinder where k equals to 0. And there is all kinds of things in a cylinder. In R3, as you imagine it, is a round case cylinder. So basically, Hellman conjectured that when you fix a measure, you only need to check 2n options for the perimeter, 2n, because you have all the sets and all the complements. And I mean, all the possible cylinders, all the possible complements, and one of them, whichever the smallest one, will be the minimizer. And obviously, a very related question would be, in few of the slides that I mentioned earlier, of course, is if we could find a function in some sense sharp that would give us the Erhard type inequality or the Brunn-Minkowski type inequality specifically for symmetric convex sets that would be in some sense optimal for cylinders. I would like to emphasize that Hörmann's conjecture talks about all possible symmetric sets, not just convex, not just complements of convex, but basically, why don't we just talk about convex symmetric sets? I mean, it's hard enough. So anyway, so in my view, it's an interesting related question. And, so I think it's difficult to even make a good conjecture here, but actually I'm going to try to convince you that this function that I wrote here is maybe a reasonable, sensible candidate for such an inequality. I cannot prove it. I can make some partial progress towards it, and I can maybe convince you that this is a reasonable conjecture. So this is pretty much my goal. Any questions so far? So let me talk about a different question about symmetry and isoperimetry in the Gaussian space. So Gardner and Wavich conjectured that for any even log concave measure and for all symmetric convex sets, this inequality of the form of the Brunn-Minkowski holds, and we can raise the measure to the power 1 over n. If the measure is log concave, basically putting power 0 there is allowed, but they conjecture that you can put power 1 over n there. So Tkach and Nayar actually showed that you can't replace the symmetry assumption with, say, just sets containing the origin in the interior in the Gaussian case. By the way, it's clear that you can't hope for anything like this to hold without any structural assumptions whatsoever, because your sets, if you fix one of the sets and you let the other set fly away very far to infinity, then it's going to obviously fail. So things like that you should prevent. Together with Colasanti Barsiglietti, we showed that locally near ball for rotation invariant log concave measures. Another thing, this question, it might seem unreasonable in a way, like why something like this should be true for all even log concave measures? Like this is ridiculous. Why should it be true? It's not logical at all. But actually, it's curious that it follows from something that's called the log Brunn-Minkowski conjecture on Brodkin, Ulyutsky, Young, and Young, which I'm not going to talk about at all. But that conjecture, it's much more reasonable, and it's very logical and very believable. So surprisingly, using actually, in our argument, we used also a result of Saraglu, important here. We get that, yeah, this should follow if we believe in log Brunn-Minkowski conjecture. Together with Sasha Kolesnikov, we showed that for the Gaussian measure and convex sets just containing the origin, you can have this inequality with the power 1 over 2n instead of 1 over n. So it's a weaker result. However, we don't need symmetry for it. We only need that sets contain the origin. Like I said, Tkach and Nayar said that if the sets just contain the origin, 1 over n is not possible. In fact, their upper bound was like 1 of square root of pi over 2n or something like this. But with 1 over 2n, it works. And Ashkenazis and Mashkidis recently proved a very beautiful result that shows that for all symmetric convex sets KNL, for the Gaussian measure, indeed this conjecture of Gardner and Wavich holds. In the Gaussian case, with the power 1 over n, this inequality is true. So let me ask now a tighter question that would bring us a bit closer to Hörmann's conjecture and all those questions about isoperimetry. So a tighter question is, suppose we want to consider not just global sum power that works for all sets KNL for a given measure, but suppose we only want this inequality to hold for sufficiently large sets. Suppose KNL are, for now, let's say symmetric and convex, and suppose the measure is big enough, bigger than A. What is the smallest number that we can put then in this inequality to hold? I call it PS mu of A. And so it's not a number, it's a function. How can we estimate from below this function tightly? And it's not hard to see that, curiously enough, it's enough to only do a local estimate. If we do a local concavity power for one convex body K to be defined as a limit of the powers for which this inequality holds, then in fact, this PS number is infimum over all sets of measure exactly A of the concavity power of K. This follows because the class of sets for which mu of k is bigger than a is closed under Minkowski interpolations. I mean, it's not hard to see. What's more interesting, or less, I don't know, what's also interesting is that in principle, the lower estimate on this p mu number is completely equivalent to asking what is a perfect, precise, best function for such an inequality. And it's very easy to see. And basically, whenever we have an estimate on ps of mu a, it means that the function that's written over here, integral from 0 to s, exponential of integral 0 to t, the thing that I wrote here, gives the inequality that we need, and vice versa. In particular, from Erhard's inequality, you could see therefore, so Erhard's inequality, we don't need to prove, we already know Erhard already proved it, and who didn't prove it? I mean, there's many beautiful proofs. So from that, even without any symmetry assumptions, we immediately see, and actually Boas pointed out to me back 8 years ago or so, that this PS in the Gaussian case tends to infinity when the measure tends to infinity. So starting from some large enough measure, and I think it's a constant measure, we already get actually a pretty large estimate, lower estimate on the concavity power in this Brunn-Minkowski type inequality. And moreover, when a tends to 1, when the measure gets larger, this power tends to infinity. And curiously, the result of Sasha and I, if you analyze it, you can see that all we get there is that if a tends to 1, then the power tends to 1 over 2n. We actually made the remark that we are annoyed that, you know, that the infinity behavior we completely miss out on. And in the result of Ashkenazis and Moschidis, one can analyze, I'm sorry, by the way, I'm not sure, Moschidis maybe, I should say, somebody should correct me. I hope I'm, anyway. Okay, in this result, yeah, in this result, the limit is 2 over n. Neither of them is infinity. So could we try and get an estimate? So this is the, basically, I will formulate a couple of results. This result is simpler in the way it's written, but it's not sharp. If you think that the expression here is not simple, it's going to get worse in a moment. But one can estimate from below the concavity power of the Gaussian measure in case basically the measure of k and l is bigger than a, and k and l is symmetric and convex. Then the following function you can put in the power over there, or alternatively, if you really want, you can write this in terms of that function that I wrote with integrals. It's the exact same thing. So this power is strictly increasing on the interval 1 over n to infinity, and indeed it tends to infinity when a tends to 1. And curiously, actually, as a corollary, we get a version of Minkowski first inequality, and it's pretty curious that, you know, we wouldn't be able to get it if we had much weaker bound. And the version of Minkowski inequality is that if we consider a convex body K and we add a body L to it and take a limit, I'm not going to focus on it too much, but I mean, I'm sure the experts are familiar with this object, I guess, but we can estimate this from, in particular, surface area is partial case of this thing. We can estimate it from below by this expression. The coefficient here, note, instead of 1 over n, we get the derivative at 1 of gamma of the dilate of K. And any questions so far? Now, this is sort of the main thing that I wanted to mention. We can estimate the concavity power for a given convex body in terms of a pretty horrible expression that only depends on moments, second moments of the random vector distributed with respect to the measure, Gaussian measure restricted on K, and the norms, K norms of that vector. It's horrible, I know, but the good thing about this is that the equality holds if and only if K is this round K cylinder. Note that I initially assumed, of course, that the set K has C2 boundary, I'm not characterizing equality cases outside of the C2 boundary. And even in the C2 boundary, there are a little bit of details required to handle the fact that a little bit we need some assumptions of strict convexity at the beginning, but luckily we only need them in the inequality where we don't need to characterize equality cases in order to end up with the equality cases in the end, and everything is okay. And some basic results in PD allow us to develop. Actually, I will comment on it in a moment. Anyway, so this is an estimate on the local concavity power for arbitrary convex body in terms of, all those horrible things. But the good thing about it is that it's sharp, and it has sharp, and the equality cases are similar to the ones in Hellman's conjecture. Moreover, the cool thing about it is that it allows us to actually get exactly the value for this concavity power for all those round cylinders. Namely, if we have a round cylinder of measure A, such that the ball that we multiply by the space is of dimension k, we know exactly what the concavity power for the cylinder, this local concavity power, equals to. And here's what it equals to. Why? Because on one hand, if we want this concavity power to do what it's defined to do, in particular, we need the dilate of that set raised to the power to be concave. Because adding dilates is one of the ways we can take combinations of convex sets. And if we do that and we take this take two derivatives and compute, turns out that this expression here is exactly the same. I know, but it's exactly the same as that expression over there. It requires a little bit of integration by parts in one dimension to see why this expression is exactly the same, but it's exactly the same. And yeah, from above, you get you get exactly that bound in the case of cylinders. And I should say, of course, that in a couple of slides, I will mention a result that's a little bit clearer. Because of course, that theorem here, let me go back to the theorem here, was we get a result with equality cases, and then we see how far can we go to not lose the equality cases and get an estimate that's nice. So this was a nice attempt. I mean, no, maybe it failed, but anyway, any questions so far? So obviously the natural question is if we can take this expression and estimate it from below by the infimum of all those expressions for those round K cylinders. Because then if that was true, then combined with the theorems that I stated, that or something else maybe was true, then we would get this concavity power would be minimized on cylinders. Then we would get that this function that I wrote over here would give us the version of a Brunn-Minkowski or Ehrhard inequality for symmetric convex sets. And I haven't verified it, I haven't written it in LaTeX, but I'm pretty sure that this would give also the isoperimetric inequality as well. But I don't want to sharpen attention on that. Yeah, but this, I believe this is probably clear. Any questions so far? So let me mention a few things about, so now I'm gonna try and explain a little bit what those two theorems that I mentioned kind of come from, but very little bit. So let me mention just a few words about energy minimization. Let me recall a classical notion of torsional rigidity is particularly well studied in the case of Lebesgue measuring function f equal to 1. It's a supremum over all functions which are 0 on the boundary of the integral of the function against our fixed function f that we fixed over the average gradient of the function squared. And there is an interesting thing about it is that there is some duality here. If you want to take supremum over all functions which take the value 0 on the boundary of this ratio, it's the same as to take infimum over all functions for which I didn't write it, but luckily Max did this for me. I'll write it later. For which LU equals to F, where L is, as in Max's talk, is the generator of the measure. We are considering the measure restricted to K, but I will be talking about this generator. So, yes, there is this duality. It's very easy. It's completely general, true in all kinds of situations. Interestingly enough, it's been studied in the Lebesgue case for hundreds of years extremely extensively. There are books and books and books about it. In the Gaussian case, it hasn't been studied that much. I found exactly one paper. I'm not going to tell you the authors because I only remember one of them. I should do it. But where they study principal frequency, just in one sentence, in one remark, actually. It turns out, for instance, that we can show a Gaussian analog of Sun-Venan theorem pretty easily. Namely that if we take function f to be 1, then the torsional rigidity would be maximized on a half space. It's really not very hard. And there is actually many more things. There is a Gaussian version of the Lentz inequalities that I don't have time to talk about. There is many things that one can also do with it. I need to clear. So in fact, the point is that what we can show is that in the Gaussian case, this concavity power is bounded from below by this torsional rigidity with respect to some f function minus the variance of f plus this additional term. And here already the equality holds if and only if K is this round cylinder. And the easiest way to, there is actually several of them, but there is an easy way to estimate torsional rigidity from below given by this lemma, where we simply just take the function 1 minus the square of the K norm. This function vanishes on the boundary. So let's plug it in the supreme definition. We get a lower bound on the torsional rigidity. And miraculously enough, we don't even lose much if we estimate the gradient of the norm here in terms of the in radius. Well, I mean, we lose probably plenty, but we don't lose the equality cases. So I decided to do that, therefore. Anyway, so this is just the details. So if we consider f to be 1 minus or some constant minus the norm of K squared, we get this, horrible long theorem that I mentioned, theorem 2. And if we let f equal to 1 and just take torsional rigidity with respect to 1, we get, and do a bit more estimates here, we get this very first Gaussian theorem that I mentioned. That's all there is. It, of course, raises a few natural questions. First of all, I mentioned that we can show, it's easy to show that the torsional rigidity with respect to 1 is maximized on half spaces. Now, if we wanted the set to be, let's say, convex and symmetric, would it be maximized on a strip? It's just a mere curiosity, not related to anything here. Can we, if we take n minus x squared function, where is it minimized? Where is it maximized? No idea. There were two questions here, so I grew some number in here is often, so it doesn't matter. Completely parallel questions that I haven't had time to think much, but I am not sure it's easy. I think it's not easy. Probably is, can we bound the powers of the norm of the random vector distributed with respect to the Gaussian measure stick to the non-convex set of the K norm of it? If instead of K norm we had L2 norm, of course we know that from above it's completely trivial and K is a ball. From below, it's completely non-trivial, and it's a very difficult theorem of Latal and Lebesgue that tells us that it's a strip if K is symmetric, and it's somewhat, I don't know, trivial, not trivial. It's pretty easy also to show that if you don't have symmetry, it's half space. You just need to estimate the barycenter. Anyway, but I'm curious if you put norm of K there. I have no idea what to do there. Another thing. Instead of considering torsional rigidity, in principle, there is many different energy minimization things. I'm very curious if one could consider something that one could call like Poincare deficit. Namely, suppose we consider, well, let's just focus on the expression here on the left. Suppose we consider all possible functions v on K, for which satisfy the equation of v equal to minus v. There is many of them. If the set is strictly convex, you can solve this equation with any boundary data Neumann or Dirichlet. Can we? It's not negative because of actually things that I will say, and already Max said a lot about, and I will say a lot about as well. can we estimate it from below? One can show that actually it's also minimized surprisingly on functions which are constant on the boundary. It's surprising that it's a Dirichlet condition rather than Neumann, but that's what seems to be the case. Yeah, how to minimize it, how to maximize it, no idea. Interestingly, for the usual for the Poincare deficit without the 2 here, if you put V to be linear functions, that very interesting things happen. So somehow I don't know, I have a feeling that this is the right thing to do, but I have no idea how to do anything with it at all. So, but still, okay. Any questions so far? So let me, no, maybe I'm a bit too fast, I don't know. So let me briefly explain in a few words why round cylinders pop up naturally here. They don't pop up here. I mean, I didn't make any effort, or I didn't make almost any effort for them to deliberately pop up here. They pop up completely naturally. And they pop up for 2 reasons. Basically, cylindriness comes from the equality case characterization that I'm going to talk about in a moment in the Brunn-Minkowski inequality. Namely, let me remind you, so Max mentioned the corollary of it, but let me remind you the Brunn-Minkowski inequality itself that tells us that if we have a low-concave measure with potential V, then this inequality is a variance of any function you can bound from above by this expression over here. Moreover, now if instead of you have arbitrary V, right? Now replace this arbitrary V with V times with e to the, okay, replace e to the power minus V with e to the power minus V times the characteristic function of K. You still have like a log concave measure, even more log concave, so this should still hold. In particular, if V is x squared over 2, then you just get the Poincare inequality holds with constant 1 for any restriction for restriction of a Gaussian measure on any set. And it would be actually somewhat surprising if you don't think about it a lot. Even Mark asked about it in this concentration group we had recently. So this was all specifically for Mark. Here, how can it be true if your measure is, if your set is very close to the origin, that the measure is very close to the back, but nonetheless, miraculously, it's true. And we heard a lot in Max's talk about this as well. So cylindriness comes from equality case characterization in this inequality. Now, roundness comes from the fact that the torsional rigidity is saturated on functions which vanish on the boundary, and there is a specific function which has to be saturated on the boundary, and it gives us this cylindriness. It's these 2 statements are not, I'm simplifying things a bit, but this is roughly sort of the story. So I want to talk a little bit about this equality case characterization in the Brunn-Minkowski inequality. I'm sure it's probably known. In fact, Max mentioned a bunch of references I didn't know. And Max, I want to ask you, maybe I should cite some references that I don't know about. Here, it could be that even in this generality it's known. I mean, it's a kind of thing that's easier to prove than to search for references for. So anyway, so the idea is that if we consider any log concave function with density e to the power minus V, which is supported entirely on a Ren and is smooth, then for any smooth convex body K, we have this inequality, like I said, it's known, but the equality holds if and only if either F is constant, then obviously we don't need anything from K, or F is of this form, grad V theta plus some constant for some vector theta, and K is cylindric, namely it's a direct product of some set of smaller dimension and some space Rn minus K, and this vector theta must be in the direction of the space. Here, the case K equal to N kind of already includes the situation when F is constant. It's the same thing, that there is no such vector, but anyway, there's a picture. And any questions about this? I'm gonna 35 minutes. I'm not planning to say much more than this actually, so let me just briefly explain why this is the case. Max already explained the proof of Brunn-Minkowski inequality using the semi-group and Bakr-Yemery estimate. So here's, you will learn in these 2 talks in this conference, in this afternoon session, morning session, two proofs of Brunn-Minkowski inequality. If you didn't want it, I'm sorry, but so how does it go? So here is a Hörmander trick of the to prove the Brunn-Minkowski inequality. Traditionally, it's used without boundary, and the inequality it's obtained in approximation for a convex set. But here we want equality cases, so we want to do everything with boundary. And our argument relies on this very important result of Kolesnikov and Millman, which is the extension of the Riley's formula. Namely, first of all, we want to estimate the variance of a function. It's enough to assume that the function is mean zero. Otherwise, we can shift. Secondly, okay, finally, I wrote the definition of this operator, which you should have written a long time ago. Consider an arbitrary function for which function u, for which Lu is f. This is Hörmander's trick. There is, like I said, if we restrict on k rather than talk about whole space, there is a whole bunch of such functions, and you have just equality here. If you want, by the way, to see this argument written without the boundary, it's a bit simpler. You could look, for example, at the paper of Fedorowski and Clark about interpolations and things. And generally, this method it's a very good place to learn about this method. Anyway, so we write the integral of f squared in this weird way. We do something slightly weird. And we integrate the first integral by parts. Then for the second integral, we use the Riley formula proved by Kolesnikov and Millman. Like I said, a very important result. They have it in completely full generality of other Riemannian manifolds as well. So you could actually do something like this with curvature, which I'm personally not wasn't aiming for this at all. This is what you get. Okay, now you wrote all the boundary terms. Now immediately what you want is to not have any boundary terms, right? This is immediate instinct. Luckily, we can do this. Namely, we could let the normal derivative of the function u to be zero. Why? Because we assumed that the integral of f is zero, so the system is compatible in this case with zero Neumann data. Okay, let's set it to be zero, then immediately what we get is something much simpler. I repeat it on the slide. To get Brunn-Minkowski inequality now, the first guy we estimate using, I'm not sure what to call it, Gaussian inequality for Hessian of V, because positive definite matrix. We estimate the integral of the Hessian squared from below by zero. And we use convexity, I should remove this parenthesis. We use convexity to estimate from below by zero this expression, because the second fundamental form is non-negative for K, for convex body. Now if you want to characterize equality cases, you see here, luckily we don't need to worry. So if we wanted it for non-smooth bodies, then I don't know bodies. We just need to see which inequality, we need to make sure that all the inequalities become equalities. So in particular, if the Hessian is zero, then you must have that U is linear. If U is linear, F was equal to LU, which gives us that F is of opposite forms that we want. Because of the Neumann assumption on U, we have everything about the shape of K. Luckily, there is no contradiction in the first inequality and no contradiction in the third inequality in this case as well. This is it. This third inequality I find particularly interesting. If we needed to do stability, we would need to do stability in all of them. It would be much harder. And I actually find it really interesting. One can show that the equality in this last inequality does hold only if it's a cylinder. Namely, if equality holds in the third inequality, then the boundary of K can be split in, if you assume three boundaries, then it can be split into two parts. One where the normal vector is orthogonal to fixed vector, if you use linear here. Second is where the second fundamental form is singular, in particular, the Gaussian curvature is zero. If it's a three, it means Gaussian curvature is zero everywhere. There is a theorem of Pogorelov, Nirenberg, Hartmann, and Massey, which says that if the Gaussian curvature is zero, then it has to be cylinder. But yeah, stability in this, I have no idea. Like, and it's a much simpler statement also. So yeah, something very curious in my view. That's it about the Gaussian measure. Any questions? So now I'm about to say just a few more theorems in the non-Gaussian case. I'll just say them very quickly. So for any log concave measure, if we have a log concave measure with twice differentiable density, if only we assume that the Hessian of V is uniformly stickily non-singular, which is, let's say, it's a strong assumption, but Max used it all the time. So let's say I don't feel bad. If he's using it, I'm not gonna feel bad. Then we have that the power in this inequality tends to infinity, as well as so like I said, Erhard's inequality guarantees that it tends to infinity. For other measures, we don't have Erhard's inequality, but nonetheless, we see that it tends to infinity. This is for symmetric convex sets. In a particular case, when the measure has density of the form e to the power minus the norm to the power p, it's a particular example of a log concave measure. We can estimate uniformly from below the concavity power by some constant, which is n to the power minus p plus 6 over 2. Horrible constant. I'm going to comment on this in a moment. But it's a uniform estimate. In some cases, it improves. In particular, it improves a lot for measures whose density is a p norm to the power p for p between 0 and 1, for p between 1 and 2. In this case, we get up to a logarithmic error, something of order 1 over n. So the best thing we can hope is 1 over n. Actually, I didn't comment on it, but this conjecture of Livshyts, it's about 1 over n because it's actually, we can't hope for anything better. Because near the origin, you get you approximate the back measure. So here we get up to a constant and logarithmic error, something of order 1 over n, and it builds up on estimates that are similar to all those estimates I mentioned before, and also the work of Barth and Clark. And this is my last slide. The theorem from 2 slides ago is based on the estimate that I believe, again, similarly to how the equality cases of Brest complete, but probably known to experts, is definitely known to experts. If we consider the Poincare constant of restriction of any isotropic log concave measure mu on arbitrary symmetric convex body K to be defined as in the first line of the slide, the best constant in the Poincare inequality, we can estimate it from above by something of order n to the power 5/4. Actually, if it's rotation variant, it's 3/4. And so if this is not hard, this is quite not hard, based on the obviously the estimate on the KLS conjecture by Liebenthal, which built up on the work on the very difficult work well done. So let me just remark that if we could get n here rather than n to the power 5/4, this would have been the end of it here. And the example would be, for example, if we take a random polytope isotropic with diameter n and take the log concave measure uniform on it and take restriction of it on some thin tube near the diameter, we would get something of order n. And this extra n to 1/4 again comes from the fact that, well, we don't know KLS conjecture. So if KLS conjecture was true, then we would have found n. Here, it's not hard. I'm curious if it's equivalent. And again, I'm sure that experts here would be like, of course, yes, or of course no. I mean, I don't know. But I'm kind of curious if it's true that if we can get the bound of every restriction is of order n, then necessarily Poincare constant of the isotropic measure log concave would be constant. Either way, that's it. Thank you very much.
Thank you very much, Galyna. Are there any questions, Galyna? Actually, I have one question. May I ask about Hellman's conjecture? So it is about the Gaussian measure. You have this phase transition of depending on the volume of the set. I think it was called A in your formulation. So is there like n jumps in the shape, or the dimension of the cylinder and the space jump by one? And you know, of course, there are similar conjectures for isoperimetric problems, say, for example, on the torus and the cube. And my question is whether you can find some direct relation between at least these conjectures. So, for example, there is this trivial map, one Livshyts map that pushes forward the Gaussian to the uniform measure on the cube, this CDF map. Maybe, I don't know, maybe you can get, for Hellman's conjecture, something on something equivalent that isoperimetric conjecture on the cube. The fact that you get these Cartesian products of a piece of one dimension and the full
So this
thing
is extremely interesting. What conjecture on the cube are you talking about? Because I don't know.
So if you have, if you look at just the same problem on the cube. So you fix
Symmetry?
No, actually no. But no, it's not symmetric. But if you fix the measure of a set with some number between 0 and 1, you want just to minimize the perimeter. So there are
Then
kind
it's
of
a corner.
Yeah, so there are some jumps kind of. If it's 1/2, then you get the half cube, but at some point it sticks here, it sticks there, and same thing on the toes. So you have like n jumps, exactly like these n jumps that you have here in the Hellman's conjecture. Now, so just curious
Really?
if you can, yeah, I think that I don't think it's proven, but I guess it's conjecture.
This is interesting. Yeah, I'd never thought about it. Maybe exactly the symmetric version would be relevant there.
You're right that, yeah, you're probably right that symmetric is yeah, probably my question is not so good because the symmetry assumption is not used.
No. It could be that this. I mean, it depends on what the map is. If you could send me some links, it would be good. Actually, it's very interesting.
Sure.
I don't really know.
Sure. Any other questions?
Yeah. So maybe I'll ask. But first, maybe I'll say something about what you asked because I have thought about this, worked on this. So by the way, so the natural analog is looking at the conjecture for real projective space, because just as we know there is an intimate relation between the Gaussian measure and the sphere, then for Gaussian measure for symmetric sets, there's the natural finite dimensional case is RPN, and there again the conjecture is exactly that. It's what are called Clifford tori, which are exactly cylinders in the real projective setting, and
but
it's
this
of course
this is stronger than Hellman's, right? This is in the limit case you get the Hellman's conjecture.
And is there direct
relation?
relation?
Than Hellman's conjecture for the Gaussian measure. No, I mean, if you just
of course, and exactly the same argument if you could prove it for a real projective space. So it's not in dimension 3, but not in higher dimension in general for real projective space. Anyway, so this is just to say something about what you asked was Galyna. But in your just a few slides ago, you analyzed the equality cases in Braskamp-Leib, but just the version of the proof of Braskamp-Leib that you gave. What is the difference between what we do in the paper with Sasha and what you showed? Is there a difference?
Which paper? You're talking about the Brunn-Minkowski paper? You prove a different inequality?
No. Our proof of the Braskamp-Leib inequality, which via the Rayleigh formula. I mean, you said you know the paper very well, so you remember we proved the Braskamp-Leib.
I thought you proved the Brunn-Minkowski. I will look again and
proved various things, and anyway, but one of them was indeed Braskamp-Leib with respect to CDKN, any KN, but that was the first paper. Okay, anyway, the history of the paper is.
Okay,
there was one post on the archive, and then we split it into 2 papers. But never mind. The first application we had is indeed a proof of Braskamp-Leib. No equality conditions at all. I mean, we didn't care about equality conditions.
Okay, so for me, this was an auxiliary result to get the equality conditions. And thank you very much. I will definitely give the credit. I was planning to just give the credit
I'm
to
just asking, is there anything different than what we do there? I mean.
Probably not. If you I need to check.
I couldn't tell, but it looks.
No, okay, here it's easy. It's very easy, but it's not about like for
I
me
agree
it was
that it's
about
very
the equality
easy,
case. Sure. No, I mean modulo your beautiful formula, obviously. But so if you look at actually the paper of Boas and Dario, they have this argument outlined for without the boundary, right? You can do the same thing without the boundary, approximate the boundary with a function. If you don't care about the equality cases, right? It's called Hörmander's proof. They call it Hörmander's proof. I don't know. Boas should comment. Maybe he knows better. But it's much shorter. You don't need the Rayleigh formula. You just need you only need actually. It's obviously right. Okay. So I believe so. I'm sorry if I missed a reference on your paper. I should have probably said because I just forgot about this.
Anyway, I thought you knew.
it's impossible to remember everything. I'm so sorry. I'm really sorry.
No problem, no problem. So just to set the thing straight, the Rayleigh formula is indeed Rayleigh's formula. This is 40-year-old formula. Our version was just, we in fact were, there was another version of this generalized, it was a generalized case due to Ding and I forgot someone else. And we basically did one additional integration by parts to get it to the form that you wrote. It's just integration by parts over Buckner's formula. There's nothing more to that.
Just so
and indeed, the method goes back at least to Hörmander, the L2 method, for proving all of these many inequalities. There's no need to praise the formula. The point was the applications of the formula. And anyway, I'll send you the link to this
sure.
paper that got split into 2 papers.
Okay. Indeed. So this proof without the boundary, very classical. I guess with the boundary, Amanda and Sasha did it. Equality cases, you can analyze it pretty easily from this. I'm sorry that I forgot that part of the paper. I didn't look at it. I'm sorry. I don't know. I can tell you. I found the paper of Boas and Dyer, and for me this was like, okay, then everything else is straightforward, and I didn't look at it. I'm sorry.
No, it's their fault that they did reference us. I'm kidding, Boas. I'm kidding.
They were like years before you.
It's fine. It's complete.
It was way before you.
I'm not sure.
Actually, I don't know. You were 2018. That was.
No. That's 2013. It was on the archive in 2013. It's published.
Your paper is Sasha.
Yes, it's. Anyway, there's a history about the publishing, but whatever.
Right, with the Brunn-Minkowski. It was before my. Okay, I see. I didn't say also. Sorry, I didn't give you credit. I didn't give me credit either here. That actually, I also had a proof of Brunn-Minkowski inequality but only in dimension 2 in my thesis. But that was 2015. But that was using harmonic analysis from the local versions. But okay, I see. So that was okay. You were fair enough.
Any further questions? More questions about credit? Because I think that the credit for this great lecture should go to Galyna. So let me thank her again. And we convene at 2 p.m. In the meanwhile, if you want, I think there is some link to gather.town. I think Omayed put a link to this thing. So if you want to hang around, then you can go there. And other than that, the conference resumes 2 p.m. Thank you and bye-bye.